Chapter 8 of The Outline of Science. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. The Outline of Science, Volume 1, by J. Arthur Thomson. Chapter 8, Foundations of the Universe, the World of Atoms. Most people have heard of the Oriental race which puzzled over the foundations of the universe and decided that it must be supported on the back of a giant elephant. But the elephant! They put it on the back of a monstrous tortoise, and there they let the matter end. If every animal in nature had been called upon, they would have been no nearer a foundation. Most ancient peoples, indeed, made no effort to find a foundation. The universe was a very compact little structure, mainly composed of the earth and the great canopy over the earth which they called the sky. They left it, as a whole, floating in nothing. And in this the ancients were wiser than they knew. Things do not fall down unless they are pulled down by that mysterious force which we call gravitation. The earth, it is true, is pulled by the sun, and would fall into it, but the earth escapes this fiery fate by circulating at great speed round the sun. The stars pull each other, but it has already been explained that they meet this by traveling rapidly in gigantic orbits. Yet we do, in a new sense of the word, need foundations of the universe. Our mind craves for some explanation of the matter out of which the universe is made. For this explanation we turn to modern physics and chemistry. Both these sciences study, under different aspects, matter and energy, and between them they have put together a conception of the fundamental nature of things which marks an epoch in the history of human thought. The bricks of the cosmos. More than 2,000 years ago the first men of science, the Greeks of the cities of Asia Minor, speculated on the nature of matter. You can grind a piece of stone into dust. You can divide a spoonful of water into as many drops as you like. Apparently you can go on dividing as long as you have got apparatus fine enough for the work. But there must be a limit, these Greeks said, and so they supposed that all matter was ultimately composed of minute particles which were indivisible. That is the meaning of the Greek word atom. Like so many other ideas of these brilliant early Greek thinkers, the atom was a sound conception. We know today that matter is composed of atoms. But science was then so young that the way in which the Greeks applied the idea was not very profound. A liquid or a gas, they said, consisted of round, smooth atoms, which would not cling together. Then there were atoms with rough surfaces, hooky surfaces, and these stuck together and formed solids. The atoms of iron or marble, for instance, were so very hooky that, once they got together, a strong man could not tear them apart. The Greeks thought that the explanation of the universe was that an infinite number of these atoms had been moving and mixing in an infinite space during an infinite time, and had at last hit by chance on the particular combination which is our universe. This was too simple and superficial. The idea of atoms was cast aside, only to be advanced again in various ways. It was the famous Manchester chemist John Dalton who restored it in the early years of the 19th century. He first definitely formulated the atomic theory as a scientific hypothesis. The whole physical and chemical science of that century was now based upon the atom, and it is quite a mistake to suppose that recent discoveries have discredited atomism. An atom is the smallest particle of a chemical element. No one has ever seen an atom. Even the wonderful new microscope which has just been invented cannot possibly show us particles of matter which are 1,000,000 times smaller than the breadth of a hair, for that is the size of atoms. We can weigh them and measure them, though they are invisible, and we know that all matter is composed of them. It is a new discovery that atoms are not indivisible. They consist themselves of still smaller particles, as we shall see. But the atoms exist all the same, and we may still say that they are the bricks of which the material universe is built. But if we had some magical glass by means of which we could see into the structure of material things, we should not see the atoms put evenly together as bricks are in a wall. As a rule, two or more atoms first come together to form a larger particle, which we call a molecule. Single atoms do not, as a rule, exist apart from other atoms. If a molecule is broken up, the individual atoms seek to unite with other atoms of another kind, or amongst themselves. For example, 3 atoms of oxygen form what we call ozone. 2 atoms of hydrogen uniting with 1 atom of oxygen form water. It is molecules that form the mass of matter. A molecule, as it has been expressed, is a little building of which atoms are the bricks. In this way we get a useful first view of the material things we handle. In a liquid, the molecules of the liquid cling together loosely. They remain together as a body, but they roll over and away from each other. There is cohesion between them, but it is less powerful than in a solid. Put some water in a kettle over the lighted gas, and presently the tiny molecules of water will rush through the spout in a cloud of steam and scatter over the kitchen. The heat has broken their bond of association and turned the water into something like a gas, though we know that the particles will come together again as they cool and form once more drops of water. In a gas the molecules have full individual liberty. They are in a state of violent movement, and they form no union with each other. If we want to force them to enter into the loose sort of association which molecules have in a liquid, we have to slow down their individual movements by applying severe cold. That is how a modern man of science liquefies gases. No power that we have will liquefy air at its ordinary temperature. In very severe cold, on the other hand, the air will spontaneously become liquid. Some day, when the fires of the sun have sunk very low, the temperature of the earth will be less than -200 degrees centigrade. That is to say, more than 200 degrees centigrade below freezing point. It will sink to the temperature of the moon. Our atmosphere will then be an ocean of liquid air, 35 feet deep, lying upon the solidly frozen masses of our water oceans. In a solid the molecules cling firmly to each other. We need a force equal to 25 tons to tear asunder the molecules in a bar of iron an inch thick. Yet the structure is not solid in the popular sense of the word. If you put a piece of solid gold in a little pool of mercury, the gold will take in the mercury between its molecules, as if it were porous, like a sponge. The hardest solid is more like a lattice work than what we usually mean by solid, though the molecules are not fixed, like the bars of a lattice work, but are in violent motion. They vibrate about equilibrium positions. If we could see right into the heart of a bit of the hardest steel, we should see billions of separate molecules, at some distance from each other, all moving rapidly to and fro. This molecular movement can, in a measure, be made visible. It was noticed by a microscopist named Brown that in a solution containing very fine suspended particles, the particles were in constant movement. Under a powerful microscope these particles are seen to be violently agitated. They are each independently darting hither and thither somewhat like a lot of billiard balls on a billiard table, colliding and rebounding about in all directions. Thousands of times a second these encounters occur, and this lively commotion is always going on. This incessant colliding of one molecule with another is the normal condition of affairs. Not one of them is at rest. The reason for this has been worked out, and it is now known that these particles move about because they are being incessantly bombarded by the molecules of the liquid. The molecules cannot, of course, be seen, but the fact of their incessant movement is revealed to the eye by the behavior of the visible suspended particles. This incessant movement in the world of molecules is called the Brownian motion, and is a striking proof of the reality of molecular motions. The wonder world of atoms. The exploration of this wonder world of atoms and molecules by the physicists and chemists of today is one of the most impressive triumphs of modern science. Quite apart from radium and electrons and other sensational discoveries of recent years, the study of ordinary matter is hardly inferior, either in interest or audacity, to the work of the astronomer. And there is the same foundation in both cases, marvelous apparatus, and trains of mathematical reasoning that would have astonished Euclid or Archimedes. Extraordinary, therefore, as are some of the facts and figures we are now going to give in connection with the minuteness of atoms and molecules, let us bear in mind that we owe them to the most solid and severe processes of human thought. Yet the principle can in most cases be made so clear that the reader will not be asked to take much on trust. It is, for instance, a matter of common knowledge that gold is soft enough to be beaten into gold leaf. It is a matter of common sense, one hopes, that if you beat a measured cube of gold into a leaf 6 inches square, the mathematician can tell the thickness of that leaf without measuring it. As a matter of fact, a single grain of gold has been beaten into a leaf 75 inches square. Now the mathematician can easily find that when a single grain of gold is beaten out to that size, the leaf must be 1/367,000th of an inch thick, or about 1,000 times thinner than the paper on which these words are printed. Yet the leaf must be several molecules thick. The finest gold leaf is, in fact, too thick for our purpose, and we turn with a new interest to that toy of our boyhood, the soap bubble. If you carefully examine one of these delicate films of soapy water, you notice certain dark spots or patches on them. These are the thinnest parts, and by two quite independent methods, one using electricity and the other light, we have found that at these spots the bubble is less than 3/millionths of an inch thick. But the molecules in the film cling together so firmly that they must be at least 20 or 30 deep in the thinnest part. A molecule, therefore, must be far less than the 3/millionths of an inch thick. We found next that a film of oil on the surface of water may be even thinner than a soap bubble. Professor Perrin, the great French authority on atoms, got films of oil down to the 50/millionth of an inch in thickness. He poured a measured drop of oil upon water. Then he found the exact limits of the area of the oil sheet by blowing upon the water a fine powder which spread to the edge of the film and clearly outlined it. The rest is safe and simple calculation, as in the case of the beaten grain of gold. Now this film of oil must have been at least 2 molecules deep, so a single molecule of oil is considerably less than 100/millionth of an inch in diameter. Innumerable methods have been tried, and the result is always the same. A single grain of indigo, for instance, will color a ton of water. This obviously means that the grain contains billions of molecules which spread through the water. A grain of musk will scent a room, pour molecules into every part of it for several years, yet not lose 1/millionth of its mass in a year. There are 100 ways of showing the minuteness of the ultimate particles of matter, and some of these enable us to give definite figures. On a careful comparison of the best methods, we can say that the average molecule of matter is less than the 1/125 millionth of an inch in diameter. In a single cubic centimeter of air, a globule about the size of a small marble, there are 30 million trillion molecules. And since the molecule is, as we saw, a group or cluster of atoms, the atom itself is smaller. Atoms, for reasons which we shall see later, differ very greatly from each other in size and weight. It is enough to say that some of them are so small that it would take 400 million of them in a line to cover an inch of space, and that it takes at least a quintillion atoms of gold to weigh a single gram. 5 million atoms of helium could be placed in a line across the diameter of a full stop. The energy of atoms. And this is only the beginning of the wonders that were done with ordinary matter, quite apart from radium and its revelations, to which we will come presently. Most people have heard of atomic energy and the extraordinary things that might be accomplished if we could harness this energy and turn it to human use. A deeper and more wonderful source of this energy has been discovered in the last 20 years, but it is well to realize that the atoms themselves have stupendous energy. The atoms of matter are vibrating or gyrating with extraordinary vigor. The piece of cold iron you hold in your hand, the bit of brick you pick up, or the penny you take from your pocket is a colossal reservoir of energy, since it consists of trillions of moving atoms. To realize the total energy, of course, we should have to witness a transformation such as we do in atoms of radioactive elements, about which we shall have something to say presently. If we put a grain of indigo in a glass of water, or a grain of musk in a perfectly still room, we soon realize that molecules travel. Similarly, the fact that gases spread until they fill every empty available space shows definitely that they consist of small particles traveling at great speed. The physicist brings his refined methods to bear on these things, and he measures the energy and velocity of these infinitely minute molecules. He tells us that molecules of oxygen, at the temperature of melting ice, travel at the rate of about 500 yards a second, more than a quarter of a mile a second. Molecules of hydrogen travel at 4 times that speed, or 3 times the speed with which a bullet leaves a rifle. Each molecule of the air, which seems so still in the house on a summer's day, is really traveling faster than a rifle bullet does at the beginning of its journey. It collides with another molecule every 20,000th of an inch of its journey. It is turned from its course 5 billion times in every second by collisions. If we could stop the molecules of hydrogen gas and utilize their energy as we utilize the energy of steam or the energy of the water at Niagara, we should find enough in every gram of gas, about 2/1000th of a pound, to raise 1/3 of a ton to a height of 40 inches. I have used for comparison the speed of a rifle bullet, and in an earlier generation people would have thought it impossible even to estimate this. It is, of course, easy. We put 2 screens in the path of the bullet, one near the rifle and the other some distance away. We connect them electrically and use a fine time-recording machine, and the bullet itself registers the time it takes to travel from the first to the second screen. Now this is very simple and superficial work in comparison with the system of exact and minute measurements which the physicist and chemist use. In one of his interesting works, Mr. Charles R. Gibson gives a photograph of 2 exactly equal pieces of paper in the opposite pans of a fine balance. A single word has been written in pencil on one of these papers, and that little scraping of lead has been enough to bring down the scale. The spectroscope will detect a quantity of matter 4 million times smaller even than this, and the electroscope is 1,000,000 times still more sensitive than the spectroscope. We have a heat measuring instrument, the bolo, which makes the best thermometer seem early Victorian. It records the millionth of a degree of temperature. It is such instruments, multiplied by the score, which enable us to do the fine work recorded in these pages. The Discovery of X-rays and Radium. The Discovery of Sir William Crookes. But these wonders of the atom are only a prelude to the more romantic and far-reaching discoveries of the new physics, the wonders of the electron. Another and the most important phase of our exploration of the material universe opened with the discovery of radium in 1898. In the discovery of radioactive elements, a new property of matter was discovered. What followed on the discovery of radium and of the X-rays we shall see. As Sir Ernest Rutherford, one of our greatest authorities, recently said, the new physics has dissipated the last doubt about the reality of atoms and molecules. The closer examination of matter which we have been able to make shows positively that it is composed of atoms. But we must not take the word now in its original Greek meaning, an indivisible thing. The atoms are not indivisible. They can be broken up. They are composed of still smaller particles. The discovery that the atom was composed of smaller particles was the welcome realization of a dream that had haunted the imagination of the 19th century. Chemists said that there were about 80 different kinds of atoms, different kinds of matter, but no one was satisfied with the multiplicity. Science is always aiming at simplicity and unity. It may be that science has now taken a long step in the direction of explaining the fundamental unity of all the matter. The chemist was unable to break up these elements into something simpler, so he called their atoms indivisible in that sense. But one man of science after another expressed the hope that we would yet discover some fundamental matter of which the various atoms were composed, one primordial substance from which all the varying forms of matter have been evolved or built up. Prout suggested this at the very beginning of the century, when atoms were rediscovered by Dalton. Father Secchi, the famous Jesuit astronomer, said that all the atoms were probably evolved from ether, and this was a very favoured speculation. Sir William Crookes talked of protheal as the fundamental substance. Others thought hydrogen was the stuff out of which all the other atoms were composed. The work which finally resulted in the discovery of radium began with some beautiful experiments of Professor, later Sir William, Crookes in the 80s. It had been noticed in 1869 that a strange coloring was caused when an electric charge was sent through a vacuum tube. The walls of the glass tube began to glow with a greenish phosphorescence. A vacuum tube is one from which nearly all the air has been pumped, although we can never completely empty the tube. Crookes used such ingenious methods that he reduced the gas in his tubes until it was 20 million times thinner than the atmosphere. He then sent an electric discharge through and got very remarkable results. The negative pole of the electric current, the cathode, gave off rays which faintly lit the molecules of the thin gas in the tube and caused a pretty fluorescence on the glass walls of the tube. What were these rays? Crookes at first thought they corresponded to a new or fourth state of matter. Hitherto we had only been familiar with matter in the three conditions of solid, liquid, and gaseous. Now Crookes really had the great secret under his eyes, but about 20 years elapsed before the true nature of these rays was finally and independently established by various experiments. The experiments proved that the rays consisted of a stream of negatively charged particles traveling with enormous velocities from 10,000 to 100,000 miles a second. In addition, it was found that the mass of each particle was exceedingly small, about 1/1800th of the mass of a hydrogen atom, the lightest atom known to science. These particles, or electrons as they are now called, were being liberated from the atom. The atoms of matter were breaking down in Crookes' tubes. At that time, however, it was premature to think of such a thing, and Crookes preferred to say that the particles of the gas were electrified and hurled against the walls of the tube. He said that it was ordinary matter in a new state, radiant matter. Another distinguished man of science, Leonard, found that when he fitted a little plate of aluminum in the glass wall of the tube, the mysterious rays passed through this as if it were a window. They must be waves in the ether, he said. The Discovery of Xrays. So the story went on from year to year. We shall see in a moment to what it led. Meanwhile, the next great step was when, in 1895, Roentgen discovered the X-rays, which are now known to everybody. He was following up the work of Leonard, and he one day covered a Crookes tube with some black stuff. To his astonishment, a prepared chemical screen which was near the tube began to glow. The rays had gone through the black stuff, and on further experiments he found that they would go through stone, living flesh, and all sorts of opaque substances. In a short time the world was astonished to learn that we could photograph the skeleton in a living man's body, locate a penny in the interior of a child that had swallowed one, or take an impression of a coin through a slab of stone. And what are these X-rays? They are not a form of matter. They are not material particles. X-rays were found to be a new variety of light, with a remarkable power of penetration. We have seen what the spectroscope reveals about the varying nature of light wavelengths. Light waves are set up by vibrations in ether, and, as we shall see, these ether disturbances are all of the same kind. They only differ as regards wavelengths. The X-rays which Roentgen discovered, then, are light, but a variety of light previously unknown to us. They are ether waves of very short length. X-rays have proved of great value in many directions, as all the world knows, but that we need not discuss at this point. Let us see what followed Roentgen's discovery. We refer throughout to the ether because, although modern theories dispense largely with this conception, the theories of physics are so inextricably interwoven with it that it is necessary, in an elementary exposition, to assume its existence. The modern view will be explained later in the article on Einstein's theory. While the world wondered at these marvels, the men of science were eagerly following up the next clue to the mystery of matter, which was exercising the mind of Crookes and other investigators. In 1896, Becquerel brought us to the threshold of the great discovery. Certain substances are phosphorescent. They become luminous after they have been exposed to sunlight for some time, and Becquerel was trying to find if any of these substances gave rise to X-rays. One day he chose a salt of the metal uranium. He was going to see if, after exposing it to sunlight, he could photograph a cross with it through an opaque substance. He wrapped it up and laid it aside to wait for the sun, but he found the uranium salt did not wait for the sun. Some strong radiation from it went through the opaque covering and made an impression of the cross upon the plate underneath. Light or darkness was immaterial. The mysterious rays streamed night and day from the salt. This was something new. Here was a substance which appeared to be producing X-rays. The rays emitted by uranium would penetrate the same opaque substances as the X-rays discovered by Roentgen. Discovery of Radium. Now, at the same time as many other investigators, Professor Curie and his Polish wife took up the search. They decided to find out whether the emission came from the uranium itself or from something associated with it, and for this purpose they made a chemical analysis of great quantities of minerals. They found a certain kind of pitchblende which was very active, and they analyzed tons of it, concentrating always on the radiant element in it. After a time, as they successively worked out the non-radiant matter, the stuff began to glow. In the end they extracted from 8 tons of pitchblende about half a teaspoonful of something that was 1,000,000 times more radiant than uranium. There was only one name for it: radium. That was the starting point of the new development of physics and chemistry. From every laboratory in the world came a cry for radium salts, as pure radium was too precious, and hundreds of brilliant workers fastened on the new element. The inquiry was broadened, and as year followed year, one substance after another was found to possess the power of emitting rays, that is, to be radioactive. We know today that nearly every form of matter can be stimulated to radioactivity, which, as we shall see, means that its atoms break up into smaller and wonderfully energetic particles which we call electrons. This discovery of electrons has brought about a complete change in our ideas in many directions. So instead of atoms being indivisible, they are actually dividing themselves spontaneously and giving off throughout the universe tiny fragments of their substance. We shall explain presently what was later discovered about the electron. Meanwhile, we can say that every glowing metal is pouring out a stream of these electrons. Every arc lamp is discharging them. Every clap of thunder means a shower of them. Every star is flooding space with them. We are witnessing the spontaneous breaking up of atoms, atoms which have been thought to be indivisible. The sun not only pours out streams of electrons from its own atoms, but the ultraviolet light which it sends to the earth is one of the most powerful agencies for releasing electrons from the surface atoms of matter on the earth. It is fortunate for us that our atmosphere absorbs most of this ultraviolet or invisible light of the sun, a kind of light which will be explained presently. It has been suggested that, if we received the full flood of it from the sun, our metals would disintegrate under its influence, and this steel civilization of ours would be impossible. But we are here anticipating, we are going beyond radium to the wonderful discoveries which were made by the chemists and physicists of the world who concentrated upon it. The work of Professor and Madame Curie was merely the final clue to guide the great search. How it was followed up, how we penetrated into the very heart of the minute atom and discovered new and portentous mines of energy, and how we were able to understand not only matter but electricity and light, will be told in the next chapter. The discovery of the electron and how it effected a revolution in ideas. What the discovery of radium implied was only gradually realized. Radium captivated the imagination of the world. It was a boon to medicine, but to the man of science it was at first a most puzzling and most attractive phenomenon. It was felt that some great secret of nature was dimly unveiled in its wonderful manifestations, and there now concentrated upon it as gifted a body of men, conspicuous among them Sir J. Thomson, Sir Ernest Rutherford, Sir W. Ramsay, and Professor Soddy, as any age could boast, with an apparatus of research so far beyond that of any other age as the Aquitania is beyond a Roman galley. Within 5 years the secret was fairly mastered. Not only were all kinds of matter reduced to a common basis, but the forces of the universe were brought into a unity and understood as they had never been understood before. The discovery of the electron. Physicists did not take long to discover that the radiation from radium was very like the radiation in a Crookes tube. It was quickly recognized, moreover, that both in the tube and in radium and other metals, the atoms of matter were somehow breaking down. However, the first step was to recognize that there were 3 distinct and different rays that were given off by such metals as radium and uranium. Sir Ernest Rutherford christened them after the first 3 letters of the Greek alphabet, the alpha, the beta, and gamma rays. We are concerned chiefly with the second group, and purpose here to deal with that group only. Footnote: the alpha rays were presently recognized as atoms of helium gas, shot out at the rate of 12,000 miles a second. The gamma rays are waves, like the X-rays, not material particles. They appear to be a type of X-rays. They possess the remarkable power of penetrating opaque substances. They will pass through a foot of solid iron, for example. End of footnote. The beta rays, as they were at first called, have proved to be one of the most interesting discoveries that science ever made. They proved what Crookes had surmised about the radiations he discovered in his vacuum tube. But it was not a fourth state of matter that had been found, but a new property of matter, a property common to all atoms of matter. The beta rays were later christened electrons. They are particles of disembodied electricity, here spontaneously liberated from the atoms of matter. Only when the electron was isolated from the atom was it recognized for the first time as a separate entity. Electrons, therefore, are a constituent of the atoms of matter, and we have discovered that they can be released from the atom by a variety of agencies. Electrons are to be found everywhere, forming a part of every atom. An electron, Sir William Bragg says, can only maintain a separate existence if it is traveling at an immense rate, from 1/300th of the velocity of light upwards, that is to say, at least 600 miles a second or thereabouts. Otherwise the electron sticks to the first atom it meets. These amazing particles may travel with the enormous velocity of from 10,000 to more than 100,000 miles a second. It was first learned that they are of an electrical nature because they are bent out of their normal path if a magnet is brought near them. And this fact led to a further discovery, to one of those sensational estimates which the general public is apt to believe to be founded on the most abstruse speculations. The physicist set up a little chemical screen for the beta rays to hit, and he so arranged his tube that only a narrow sheaf of the rays poured onto the screen. He then drew this sheaf of rays out of its course with a magnet, and he accurately measured the shift of the luminous spot on the screen where the rays impinged on it. But when he knows the exact intensity of his magnetic field, which he can control as he likes, and the amount of deviation it causes, and the mass of the moving particles, he can tell the speed of the moving particles, which he thus diverts. These particles were being hurled out of the atoms of radium, or from the negative pole in a vacuum tube, at a speed which in good conditions reached nearly the velocity of light, that is, nearly 186,000 miles a second. Their speed has, of course, been confirmed by numbers of experiments, and another series of experiments enabled physicists to determine the size of the particles. Only one of these need be described to give the reader an idea how men of science arrived at their more startling results. Fog, as most people know, is thick in our great cities because the water vapor gathers on the particles of dust and smoke that are in the atmosphere. This fact was used as the basis of some beautiful experiments. Artificial fogs were created in little glass tubes by introducing dust in various proportions for supersaturated vapor to gather on. In the end it was possible to cause tiny drops of rain, each with a particle of dust at its core, to fall upon a silver mirror and be counted. It was a method of counting the quite invisible particles of dust in the tube, and the method was now successfully applied to the new rays. Yet another method was to direct a slender stream of the particles upon a chemical screen. The screen glowed under the cannonade of particles, and a powerful lens resolved the glow into distinct sparks which could be counted. In short, a series of the most remarkable and beautiful experiments, checked in all the great laboratories of the world, settled the nature of these so-called rays. They were streams of particles more than 1,000 times smaller than the smallest known atom. The mass of each particle is, according to the latest and finest measurements, 1,845th of that of an atom of hydrogen. The physicist has not been able to find any character except electricity in them, and the name electrons has been generally adopted. The key to many mysteries. The electron is an atom of disembodied electricity. It occupies an exceedingly small volume, and its mass is entirely electrical. These electrons are the key to half the mysteries of matter. Electrons in rapid motion, as we shall see, explain what we mean by an electric current, not so long ago regarded as one of the most mysterious manifestations in nature. What a wonder, then, have we here, says Professor R.K. Duncan, an innocent-looking little pinch of salt, and yet possessed of special properties utterly beyond even the fanciful imaginings of man of past time. For nowhere do we find in the records of thought even the hint of the possibility of things which we now regard as established fact. This pinch of salt projects from its surface bodies, that is, electrons, possessing the inconceivable velocity of over 100,000 miles a second, a velocity sufficient to carry them, if unimpeded, 5 times around the earth in a second, and possessing with this velocity masses 1,000 times smaller than the smallest atom known to science. Furthermore, they are charged with negative electricity. They pass straight through bodies considered opaque with a sublime indifference to the properties of the body, with the exception of its mere density. They cause bodies which they strike to shine out in the dark. The effect of photographic plate. They render the air a conductor of electricity. They cause clouds in moist air. They cause chemical action and have a peculiar physiological action. Who today shall predict the ultimate service to humanity of the beta rays from radium? End of this part of Chapter 8. Chapter 8, Part 2 of The Outline of Science. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. The Outline of Science, Volume 1, by J. Arthur Thomson. Chapter 8, Part 2. The Electron Theory, or the New View of Matter. The Structure of the Atom. There is general agreement amongst all chemists, physicists, and mathematicians upon the conclusions which we have so far given. We know that the atoms of matter are constantly, either spontaneously or under stimulation, giving off electrons or breaking up into electrons, and they therefore contain electrons. Thus we have now complete proof of the independent existence of atoms and also of electrons. When, however, the man of science tries to tell us how electrons compose atoms, he passes from facts to speculation, and very difficult speculation. Take the letter O, as it is printed on this page. In a little bubble of hydrogen gas no larger than that letter there are trillions of atoms, and they are not packed together, but are circulating as freely as dancers in a ballroom. We are asking the physicist to take one of these minute atoms and tell us how the still smaller electrons are arranged in it. Naturally, he can only make mental pictures, guesses, or hypotheses, which he tries to fit to the facts, and discards when they will not fit. At present, after nearly 20 years of critical discussion, there are two chief theories of the structure of the atom. At first, Sir J. Thomson imagined the electrons circulating in shells, like the layers of an onion, round the nucleus of the atom. This did not suit, and Sir E. Rutherford and others worked out a theory that the electrons circulated round a nucleus rather like the planets of our solar system revolving round the central sun. Is there a nucleus, then, round which the electrons revolve? The electron, as we saw, is a disembodied atom of electricity. We should say, of negative electricity. Let us picture these electrons all moving round in orbits with great velocity. Now it is suggested that there is a nucleus of positive electricity, attracting or pulling the revolving electrons to it, and so forming an equilibrium. Otherwise the electrons would fly off in all directions. This nucleus has been recently named the proton. We have thus two electricities in the atom. The positive equals the nucleus. The negative equals the electron. Of recent years, Dr. Langmuir has put out a theory that the electrons do not revolve round the nucleus, but remain in a state of violent agitation of some sort at fixed distances from the nucleus. But we will confine ourselves here to the facts, and leave the contending theories to scientific men. It is now pretty generally accepted that an atom of matter consists of a number of electrons, or charges of negative electricity, held together by a charge of positive electricity. It is not disputed that these electrons are in a state of violent motion or strain, and that therefore a vast energy is locked up in the atoms of matter. To that we will return later. Here, rather, we will notice another remarkable discovery which helps us to understand the nature of matter. A brilliant young man of science who was killed in the war, Mr. Moseley, some years ago showed that, when the atoms of different substances are arranged in order of their weight, they are also arranged in the order of increasing complexity of structure. That is to say, the heavier the atom, the more electrons it contains. There is a gradual building up of atoms containing more and more electrons from the lightest atom to the heaviest. Here it is enough to say that as he took element after element, from the lightest, hydrogen, to the heaviest, uranium, he found a strangely regular relation between them. If hydrogen were represented by the figure 1, helium by 2, lithium 3, and so on up to radium, then uranium should have the figure 92. This makes it probable that there are in nature 92 elements. We have found 87, and that the number Mr. Moseley found is the number of electrons in the atom of each element. That is to say, the number is arranged in order of the atomic numbers of the various elements. The new view of matter. Up to the point we have reached, then, we see what the new view of matter is. Every atom of matter, of whatever kind throughout the whole universe, is built up of electrons in conjunction with a nucleus. From the smallest atom of all, the atom of hydrogen, which consists of one electron rotating round a positively charged nucleus, to a heavy complicated atom, such as the atom of gold, constituted of many electrons and a complex nucleus, we have only to do with positive and negative units of electricity. The electron and its nucleus are particles of electricity. All matter, therefore, is nothing but a manifestation of electricity. The atoms of matter, as we saw, combine and form molecules. Atoms and molecules are the bricks out of which nature has built up everything: ourselves, the earth, the stars, the whole universe. But more than bricks are required to build a house. There are other fundamental existences, such as the various forms of energy, which give rise to several complex problems. And we have also to remember that there are more than 80 distinct elements, each with its own definite type of atom. We shall deal with energy later. Meanwhile, it remains to be said that, although we have discovered a great deal about the electron and the constitution of matter, and that while the physicists of our own day seem to see a possibility of explaining positive and negative electricity, the nature of them both is unknown. There exists the theory that the particles of positive and negative electricity, which make up the atoms of matter, are points or centers of disturbances of some kind in a universal ether, and that all the various forms of energy are, in some fundamental way, aspects of the same primary entity which constitutes matter itself. But the discovery of the property of radioactivity has raised many other interesting questions, besides that which we have just dealt with. In radioactive elements, such as uranium for example, the element is breaking down. In what we call radioactivity we have a manifestation of the spontaneous change of elements. What is really taking place is a transmutation of one element into another, from a heavier to a lighter. The element uranium spontaneously becomes radium, and radium passes through a number of other stages until it, in turn, becomes lead. Each descending element is of lighter atomic weight than its predecessor. The changing process, of course, is a very slow one. It may be that all matter is radioactive, or can be made so. This raises the question whether all matter in the universe may not undergo disintegration. There is, however, another side of the question, which the discovery of radioactivity has brought to light, and which has effected a revolution in our views. We have seen that in radioactive substances the elements are breaking down. Is there a process of building up at work? If the more complicated atoms are breaking down into simpler forms, may there not be a converse process, a building up from simpler elements to more complicated elements? It is probably the case that both processes are at work. There are some 80-odd chemical elements on the earth today. Are they all the outcome of an inorganic evolution, element giving rise to element, going back and back to some primeval stuff from which they were all originally derived infinitely long ago? Is there an evolution in the inorganic world which may be going on, parallel to that of the evolution of living things? Or is organic evolution a continuation of inorganic evolution? We have seen what evidence there is of this inorganic evolution in the case of the stars. We cannot go deeply into the matter here, nor has the time come for any direct statement that can be based on the findings of modern investigation. Taking it all together, the evidence is steadily accumulating, and there are authorities who maintain that already the evidence of inorganic evolution is convincing enough. The heavier atoms would appear to behave as though they were evolved from the lighter. The more complex forms, it is supposed, have evolved from the simpler forms. Moseley's discovery, to which reference has been made, points to the conclusion that the elements are built up one from another. Other new views. We may here refer to another new conception to which the discovery of radioactivity has given rise. Lord Kelvin, who estimated the age of the Earth at 20 million years, reached this estimate by considering the Earth as a body which is gradually cooling down, losing its primitive heat like a loaf taken from the oven, at a rate which could be calculated, and that the heat radiated by the sun was due to contraction. Uranium and radioactivity were not known to Kelvin, and their discovery has upset both his arguments. Radioactive substances, which are perpetually giving out heat, introduce an entirely new factor. We cannot now assume that the Earth is necessarily cooling down. It may even, for all we know, be getting hotter. At the 1921 meeting of the British Association, Professor Rayleigh stated that further knowledge had extended the probable period during which there had been life on this globe to about 1,000 million years, and the total age of the Earth to some small multiple of that. The Earth, he considers, is not cooling, but contains an internal source of heat from the disintegration of uranium in the outer crust. On the whole, the estimate obtained would seem to be in agreement with the geological estimates. The question, of course, cannot in the present state of our knowledge be settled within fixed limits that meet with general agreement. As we have said, there are other fundamental existences which give rise to more complex problems. The three great fundamental entities in the physical universe are matter, ether, and energy, so far as we know. Outside these there is nothing. We have dealt with matter, there remain ether and energy. We shall see that just as no particle of matter, however small, may be created or destroyed, and just as there is no such thing as empty space, ether pervades everything, so there is no such thing as rest. Every particle that goes to make up our solid earth is in a state of perpetual, unremitting vibration. Energy is the universal commodity on which all life depends. Separate and distinct as these three fundamental entities, matter, ether, and energy, may appear, it may be that, after all, they are only different and mysterious phases of an essential oneness of the universe. The future. Let us, in concluding this chapter, give just one illustration of the way in which all this new knowledge may prove to be as valuable practically as it is wonderful intellectually. We saw that electrons are shot out of atoms at a speed that may approach 160,000 miles a second. Sir Oliver Lodge has written recently that a 70th of a grain of radium discharges, at a speed 1,000 times that of a rifle bullet, 30 million electrons a second. Professor Le Bon has calculated that it would take 1,340,000 barrels of powder to give a bullet the speed of one of these electrons. He shows that the smallest French copper coin, smaller than a farthing, contains an energy equal to 80 million horsepower. A few pounds of matter contain more energy than we could extract from millions of tons of coal. Even in the atoms of hydrogen, at a temperature which we could produce in an electric furnace, the electrons spin round at a rate of nearly 100 trillion revolutions a second. Every man asks at once, will science ever tap this energy? If it does, no more smoke, no mining, no transit, no bulky fuel. The energy of an atom is of course only liberated when an atom passes from one state to another. The stored-up energy is fortunately fast-bound by the electrons being held together, as has been described. If it were not so, the earth would explode and become a gaseous nebula. It is believed that some day we shall be able to release, harness, and utilize atomic energy. I am of opinion, says Sir William Bragg, that atom energy will supply our future need. 1,000 years may pass before we can harness the atom, or tomorrow might see us with the reins in our hands. That is the peculiarity of physics. Research and accidental discovery go hand in hand. Half a brick contains as much energy as a small coal field. The difficulties are tremendous, but as Sir Oliver Lodge reminds us, there was just as much skepticism at one time about the utilization of steam or electricity. Is it to be supposed, he asks, that there can be no fresh invention, that all the discoveries have been made? More than one man of science encourages us to hope. Here are some remarkable words written by Professor Soddy, one of the highest authorities on radioactive matter, in our chief scientific weekly, Nature magazine, November 6, 1919. Quote, "The prospects of the successful accomplishments of artificial transmutation brighten almost daily. The ancients seem to have had something more than an inkling that the accomplishment of transmutation would confer upon men powers hitherto the prerogative of the gods. But now we know definitely that the material aspect of transmutation would be of small importance in comparison with the control over the inexhaustible stores of internal atomic energy to which its successful accomplishment would inevitably lead. It has become a problem, no longer redolent of the evil associations of the age of alchemy, but one big with a promise of a veritable physical renaissance of the whole world." End quote. If that promise is ever realized, the economic and social face of the world will be transformed. Before passing on to the consideration of ether, light, and energy, let us see what new light the discovery of the electron has thrown on the nature and manipulation of electricity. What is electricity? The nature of electricity. There is at least one manifestation in nature, and so late as 20 years ago it seemed to be one of the most mysterious manifestations of all, which has been in great measure explained by the new discoveries. Already, at the beginning of this century, we spoke of our age of electricity, yet there were few things in nature about which we knew less. The electric current rang our bells, drove our trains, lit our rooms, but none knew what the current was. There was a vague idea that it was a sort of fluid that flowed along copper wires as water flows in a pipe. We now suppose that it is a rapid movement of electrons from atom to atom in the wire or wherever the current is. Let us try to grasp the principle of the new view of electricity and see how it applies to all the varied electrical phenomena in the world about us. As we saw, the nucleus of an atom of matter consists of positive electricity which holds together a number of electrons or charges of negative electricity. Footnote: the words positive and negative electricity belong to the days when it was regarded as a fluid. A body overcharged with the fluid was called positive. An undercharged body was called negative. A positively electrified body is now one whose atoms have lost some of their outlying electrons, so that the positive charge of electricity predominates. The negatively electrified body is one with more than the normal number of electrons. End of footnote. This certainly tells us to some extent what electricity is and how it is related to matter, but it leaves us with the usual difficulty about fundamental realities. But we now know that electricity, like matter, is atomic in structure. A charge of electricity is made up of a number of small units or charges of a definite constant amount. It has been suggested that the two kinds of electricity, that is, positive and negative, are right-handed and left-handed vortices or whirlpools in ether, or rings in ether, but there are very serious difficulties, and we leave this to the future. What an electric current is. The discovery of these two kinds of electricity has, however, enabled us to understand very fairly what goes on in electrical phenomena. The outlying electrons, as we saw, may pass from atom to atom, and this on a large scale is the meaning of the electric current. In other words, we believe an electric current to be a flow of electrons. Let us take, to begin with, a simple electrical cell, in which a feeble current is generated, such a cell as there is in every house to serve its electric bells. In the original form, this simple sort of battery consisted of a plate of zinc and a plate of copper immersed in a chemical. Long before anything was known about electrons, it was known that, if you put zinc and copper together, you produce a mild current of electricity. We know now what this means. Zinc is a metal the atoms of which are particularly disposed to part with some of their outlying electrons. Why, we do not know, but the fact is the basis of these small batteries. Electrons from the atoms of zinc pass to the atoms of copper, and their passage is a current. Each atom gives up an electron to its neighbor. It was further found long ago that if the zinc and copper were immersed in certain chemicals, which slowly dissolved the zinc, and the two metals were connected by a copper wire, the current was stronger. In modern language, there is a brisker flow of electrons. The reason is that the atoms of zinc which are stolen by the chemical leave their detachable electrons behind them, and the zinc has therefore more electrons to pass on to the copper. Such cells are now made of zinc and carbon immersed in sal ammoniac, but the principle is the same. The flow of electricity is a flow of electrons. though we ought to repeat that they do not flow in a body, as molecules of water do. You may have seen boys place a row of bricks, each standing on one end, in such order that the first, if it is pushed, will knock over the second, the third, and so on to the last. There is a flow of movement all along the line, but each brick moves only a short distance. So an electron merely passes to the next atom, which sends on an electron to a third atom, and so on. In this case, however, the movement from atom to atom is so rapid that the ripple of movement, if we may call it so, may pass along at an enormous speed. We have seen how swiftly electrons travel. But how is this turned into power enough even to ring the bell? The actual mechanical apparatus by which the energy of the electron current is turned into sound, or heat, or light, will be described in a technical section later in this work. We are concerned here only with the principle, which is clear. While zinc is very apt to part with electrons, copper is just as obliging in facilitating their passage onward. Electrons will travel in this way in most metals, but copper is one of the best conductors. So we lengthen the copper wire between the zinc and the carbon until it goes as far as the front door and the bell, which are included in the circuit. When you press the button at the door, two wires are brought together, and the current of electrons rushes round the circuit, and at the bell its energy is diverted into the mechanical apparatus which rings the bell. Copper is a good conductor, 6 times as good as iron, and is therefore so common in electrical industries. Some other substances are just as stubborn as copper is yielding, and we call them insulators, because they resist the current instead of letting it flow. Their atoms do not easily part with electrons. Glass, vulcanite, and porcelain are very good insulators for this reason. What the dynamo does. But even several cells together do not produce the currents needed in modern industry, and the flow is produced in a different manner. As the invisible electrons pass along a wire, they produce what we call a magnetic field around the wire. They produce a disturbance in the surrounding ether. To be exact, it is through the ether surrounding the wire that the energy originated by the electrons is transmitted. To set electrons moving on a large scale, we use a dynamo. By means of the dynamo, it is possible to transform mechanical energy into electrical energy. The modern dynamo, as Professor Soddy puts it, may be looked upon as an electron pump. We cannot go into the subject deeply here. We would only say that a large coil of copper wire is caused to turn round rapidly between the poles of a powerful magnet. That is the essential construction of the dynamo, which is used for generating strong currents. We shall see in a moment how magnetism differs from electricity, and will say here only that round the poles of a large magnet there is a field of intense disturbance which will start a flow of electrons in any copper that is introduced into it. On account of the speed given to the coil of wire, its atoms enter suddenly this magnetic field, and they give off crowds of electrons in a flash. It is found that a similar disturbance is caused, though the flow is in the opposite direction, when the coil of wire leaves the magnetic field. And as the coil is revolving very rapidly, we get a powerful current of electricity that runs in alternate directions, an alternating current. Electricians have apparatus for converting it into a continuous current where this is necessary. A current, therefore, means a steady flow of the electrons from atom to atom. Sometimes, however, a number of electrons rush violently and explosively from one body to another, as in the electric spark, or the occasional flash from an electric tram or train. The grandest and most spectacular display of this phenomenon is the thunderstorm. As we saw earlier, a portentous furnace like the sun is constantly pouring floods of electrons from its atoms into space. The earth intercepts great numbers of these electrons. In the upper regions of the air, the stream of solar electrons has the effect of separating positively electrified atoms from negatively electrified ones, and the water vapor, which is constantly rising from the surface of the sea, gathers more freely round their positively electrified atoms, and brings them down as rain to the earth. Thus the upper air loses a proportion of positive electricity, or becomes negatively electrified. In the thunderstorm we get both kinds of clouds, some with large excesses of electrons and some deficient in electrons, and the tension grows until at last it is relieved by a sudden and violent discharge of electrons from one cloud to another, or to the earth, an electric spark on a prodigious scale. Magnetism. We have seen that an electric current is really a flow of electrons. Now, an electric current exhibits a magnetic effect. The surrounding space is endowed with energy which we call electromagnetic energy. A piece of magnetized iron attracting other pieces of iron to it is the popular idea of a magnet. If we arrange a wire to pass vertically through a piece of cardboard, and then sprinkle iron filings on the cardboard, we shall find that, on passing an electric current through the wire, the iron filings arrange themselves in circles round it. The magnetic force, due to the electric current, seems to exist in circles round the wire, an ether disturbance being set up. Even a single electron, when in movement, creates a magnetic field, as it is called, round its path. There is no movement of electrons without this attendant field of energy, and their motion is not stopped until that field of energy disappears from the ether. The modern theory of magnetism supposes that all magnetism is produced in this way. All magnetism is supposed to arise from the small whirling motions of the electrons contained in the ultimate atoms of matter. We cannot here go into the details of the theory, nor explain why, for instance, iron behaves so differently from other substances, but it is sufficient to say that here also the electron theory provides the key. The theory is not yet definitely proved, but it furnishes a sufficient theoretical basis for future research. The Earth itself is a gigantic magnet, a fact which makes the compass possible, and it is well known that the Earth's magnetism is affected by those great outbreaks on the sun called sunspots. Now it has been recently shown that a sunspot is a vast whirlpool of electrons, and that it exerts a strong magnetic action. There is doubtless a connection between these outbreaks of electronic activity and the consequent changes in the Earth's magnetism. The precise mechanism of the connection, however, is still a matter that is being investigated. Ether and waves. The whole material universe is supposed to be embedded in a vast medium called the ether. It is true that the notion of the ether has been abandoned by some modern physicists, but whether or not it is ultimately dispensed with, the conception of the ether has entered so deeply into the scientific mind that the science of physics cannot be understood unless we know something about the properties attributed to the ether. The ether was invented to explain the phenomena of light, and to account for the flow of energy across empty space. Light takes time to travel. We see the sun at any moment by the light that left it 8 minutes before. It has taken that 8 minutes for the light from the sun to travel that 93 million miles odd which separates it from our Earth. Besides the fact that light takes time to travel, it can be shown that light travels in the form of waves. We know that sound travels in waves. Sound consists of waves in the air, or water, or wood, or whatever medium we hear it through. If an electric bell be put in a glass jar and the air be pumped out of the jar, the sound of the bell becomes feebler and feebler until, when enough air has been taken out, we do not hear the bell at all. Sound cannot travel in a vacuum. We continue to see the bell, however, so that evidently light can travel in a vacuum. The invisible medium through which the waves of light travel is the ether, and this ether permeates all space and all matter. Between us and the stars stretch vast regions empty of all matter. But we see the stars, their light reaches us, even though it may take centuries to do so. We conceive then that it is the universal ether which conveys that light. All the energy which has reached the earth from the sun, and which, stored for ages in our coal fields, is now used to propel our trains and steamships, to heat and light our cities, to perform all the multifarious tasks of modern life, was conveyed by the ether. Without that universal carrier of energy, we should have nothing but a stagnant, lifeless world. We have said that light consists of waves. The ether may be considered as resembling, in some respects, a jelly. It can transmit vibrations. The waves of light are really excessively small ripples, measuring from crest to crest. The distance from crest to crest of the ripples in a pond is sometimes no more than an inch or two. This distance is enormously great compared to the longest of the wavelengths that constitute light. We say the longest, for the waves of light differ in length. The color depends upon the length of the light. Red light has the longest waves, and violet the shortest. The longest waves, the waves of deep red light, are 7/250,000ths of an inch in length. This is nearly twice the length of deep violet light waves, which are 1/60,000th of an inch. But light waves, the waves that affect the eye, are not the only waves carried by the ether. Waves too short to affect the eye can affect the photographic plate, and we can discover in this way the existence of waves only half the length of the deep violet waves. Still shorter waves can be discovered until we come to those excessively minute rays, the X-rays. Below the limits of visibility. But we can extend our investigations in the other direction. We find that the ether carries many waves longer than light waves. Special photographic emulsions can reveal the existence of waves 5 times longer than violet light waves. Extending below the limits of visibility are waves we detect as heat waves. Radiant heat, like the heat from a fire, is also a form of wave motion in the ether, but the waves our senses recognize as heat are longer than light waves. There are longer waves still, but our senses do not recognize them. But we can detect them by our instruments. These are the waves used in wireless telegraphy, and their length may be, in some cases, measured in miles. These waves are the so-called electromagnetic waves. Light, radiant heat, and electromagnetic waves are all of the same nature. They differ only as regards their wavelengths. End of this part of Chapter 8. Chapter 8, Part 3 of the Outline of Science. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. The Outline of Science, Volume 1, by J. Arthur Thomson. Chapter 8, Part 3. Light, visible and invisible. If light, then, consists of waves transmitted through the ether, what gives rise to the waves? Whatever sets up such wonderfully rapid series of waves must be something with an enormous vibration. We come back to the electron. All atoms of matter, as we have seen, are made up of electrons revolving in a regular orbit round a nucleus. These electrons may be affected by outside influences. They may be agitated and their speed or vibration increased. Electrons and light. The particles even of a piece of cold iron are in a state of vibration. No nerves of ours are able to feel and register the waves they emit, but your cold poker is really radiating or sending out a series of wave movements on every side. After what we saw about the nature of matter, this will surprise none. Put your poker in the fire for a time. The particles of the glowing coal, which are violently agitated, communicate some of their energy to the particles of iron in the poker. They move to and fro more rapidly, and the waves which they create are now able to affect your nerves and cause a sensation of heat. But put the poker again in the fire until its temperature rises to 500 degrees centigrade. It begins to glow with a dull red. Its particles are now moving very violently, and the waves they send out are so short and rapid that they can be picked up by the eye. We have visible light. They would still not affect a photographic plate. Heat the iron further, and the crowds of electrons now send out waves of various lengths which blend into white light. What is happening is the agitated electrons flying round in their orbits at a speed of trillions of times a second. Make the iron blue hot, and it pours out, in addition to light, the invisible waves which alter the film on the photographic plate. And beyond these there is a long range of still shorter waves, culminating in the X-rays, which will pass between the atoms of flesh or stone. Nearly 250 years ago it was proved that light traveled at least 600,000 times faster than sound. Jupiter, as we saw, has moons which circle round it. They pass behind the body of the planet and reappear at the other side. But it was noticed that, when Jupiter is at its greatest distance from us, the reappearance of the moon from behind it is 16 minutes and 36 seconds later than when the planet is nearest to us. Plainly, this was because light took so long to cover the additional distance. The distance was then imperfectly known, and the speed of light was underrated. We now know the distance, and we can easily get the velocity of light. No doubt it seems far more wonderful to discover this within the walls of a laboratory, but it was done as long ago as 1850. A cogged wheel is so mounted that a ray of light passes between two of the teeth and is reflected back from a mirror. Now, slight as is the fraction of a second which light takes to travel that distance, it is possible to give such speed to the wheel that the next tooth catches the ray of light on its return and cuts it off. The speed is increased still further until the ray of light returns to the eye of the observer through the notch next to the one by which it had passed to the mirror. The speed of the wheel was known, and it was thus possible again to gather the velocity of light. If the shortest waves are 1/67,000th of an inch in length, and light travels at 186,000 miles a second, any person can work out that about 800 trillion waves enter the eye in a second when we see violet. Sorting out light waves. The waves sent out on every side by the energetic electrons become faintly visible to us when they reach about 1/35,000th of an inch. As they become shorter and more rapid, as the electrons increase their speed, we get, in succession, the colors red, orange, yellow, green, blue, indigo, and violet. Each distinct sensation of color means a wave of different length. When they are all mingled together, as in the light of the sun, we get white light. When this white light passes through glass, the speed of the waves is lessened, and if the ray of light falls obliquely on a triangular piece of glass, the waves of different lengths part company as they travel through it, and the light is spread out in a band of rainbow color. The waves are sorted out according to their lengths in the obstacle race through the glass. Anyone may see this for himself by holding up a wedge-shaped piece of crystal between the sunlight and the eye. The prism separates the sunlight into its constituent colors, and these various colors will be seen quite readily. Or the thing may be realized in another way. If the 7 colors are painted on a wheel as shown, opposite page 280, in the proportion shown, and the wheel rapidly revolved on a pivot, the wheel will appear a dull white. The several colors will not be seen. But omit one of the colors, then the wheel, when revolved, will not appear white, but will give the impression of one color, corresponding to what the union of 6 colors gives. Another experiment will show that some bodies held up between the eye and a white light will not permit all the rays to pass through, but will intercept some. A body that intercepts all the 7 rays except red will give the impression of red, or if all the rays except violet, then violet will be the color seen. The fate of the world. Professor Soddy has given an interesting picture of what might happen when the sun's light and heat is no longer what it is. The human eye has adapted itself through the ages to the peculiarities of the sun's light, so as to make the most of that wavelength of which there is most. Let us indulge for a moment in these gloomy prognostications as to the consequences to this earth of the cooling of the sun with the lapse of ages, which used to be in vogue, but which radioactivity has so rudely shaken. Picture the fate of the world when the sun has become a dull red-hot ball, or even when it is cooled so far that it would no longer emit light to us. That does not all mean that the world would be an inky darkness, and that the sun would not emit light to the people then inhabiting this world, if any had survived and could keep themselves from freezing. To such, if the eye continued to adapt itself to the changing conditions, our blues and violets would be ultraviolet and invisible, but our dark heat would be light, and hot bodies would be luminous to them which would be dark to us. What the blue sky means. We saw in a previous chapter how the spectroscope splits up light waves into their colors, but nature is constantly splitting the light into its different lengthed waves, its colors. The rainbow, where dense moisture in the air acts as a spectroscope, is the most familiar example. A piece of mother of pearl, or even a film of oil on the street or on water, has the same effect, owing to the fine inequalities in its surface. The atmosphere all day long is sorting out the waves. The blue sky overhead means that the fine particles in the upper atmosphere catch the shorter waves, the blue waves, and scatter them. We can make a tube full of blue sky in the laboratory at any time. The beautiful pink flush on the Alps at sunrise, the red glory that lingers in the west at sunset, mean that, as the sun's rays must struggle through denser masses of air when it is low on the horizon, the long red waves are sifted out from the other shafts. Then there is the varied face of nature which, by absorbing some waves and reflecting others, weaves its own beautiful robe of color. Here and there is a black patch, which absorbs all the light. White surfaces reflect the whole of it. What is reflected depends on the period of vibration of the electrons in the particular kind of matter. Generally, as the electrons receive the flood of trillions of waves, they absorb either the long or the medium or the short, and they give us the wonderful color scheme of nature. In some cases the electrons continue to radiate long after the sunlight has ceased to fall upon them. We get from them black or invisible light, and we can take photographs by it. Other bodies, like glass, vibrate in unison with the period of the light waves, and let them stream through. Light without heat. There are substances, phosphorescent things we call them, which give out a mysterious cold light of their own. It is one of the problems of science, and one of profound practical interest. If we could produce light without heat, our gas bill would shrink amazingly. So much energy is wasted in the production of heat waves and ultraviolet waves which we do not want, that 90% or more of the power used in illumination is wasted. Would that the glowworm, or even the dead herring, would yield us its secret. Phosphorus is the one thing we know as yet that suits the purpose, and it smells. Indeed, our artificial light is not only extravagant in cost but often poor in color. The unwary person often buys a garment by artificial light, and is disgusted next morning to find in it a color which is not wanted. The color disclosed by the sun was not in the waves of the artificial light. Beyond the waves of violet light are the still shorter and more rapid waves, the ultraviolet waves, which are precious to the photographer. As every amateur knows, his plate may safely be exposed to light that comes through a red or an orange screen. Such a screen means no thoroughfare for the blue and beyond blue waves, and it is these which arrange the little grains of silver on the plate. It is the same waves which supply the energy to the little green grains of matter, chlorophyll, in the plant, preparing our food and timber for us, as will be seen later. The tree struggles upward and spreads out its leaves fan-wise to the blue sky to receive them. In our coal measures, the mighty dead forests of long ago, are vast stores of sunlight which we are prodigally using up. The X-rays are the extreme end, the highest octave of the series of waves. Their power of penetration implies that they are excessively minute, but even these have not held their secret from the modern physicist. From a series of beautiful experiments, in which they were made to pass amongst the atoms of a crystal, we learn their length. It is about the 10,000,000th of a millimeter, and a millimeter is about the 1/25th of an inch. One of the most recent discoveries, made during a recent eclipse of the sun, is that light is subject to gravitation. A ray of light from a star is bent out of its straight path when it passes near the mass of the sun. Professor Eddington tells us that we have as much right to speak of a pound of light as of a pound of sugar. Professor Eddington even calculates that the Earth receives 160 tons of light from the sun every year. Energy, how all life depends on it. As we have seen in an earlier chapter, one of the fundamental entities of the universe is matter. A second, not less important, is called energy. Energy is indispensable if the world is to continue to exist, since all phenomena, including life, depend on it. Just as it is humanly impossible to create or to destroy a particle of matter, so is it impossible to create or to destroy energy. This statement will be more readily understood when we have considered what energy is. Energy, like matter, is indestructible, and just as matter exists in various forms, so does energy. And we may add, just as we are ignorant of what the negative and positive particles of electricity which constitute matter really are, so we are ignorant of the true nature of energy. At the same time, energy is not so completely mysterious as it once was. It is another of nature's mysteries which the advance of modern science has in some measure unveiled. It was only during the 19th century that energy came to be known as something as distinct and permanent as matter itself. Forms of energy. The existence of various forms of energy had been known, of course, for ages. There was the energy of a falling stone, the energy produced by burning wood or coal or any other substance, but the essential identity of all these forms of energy had not been suspected. The conception of energy as something which, like matter, was constant in amount, which could not be created nor destroyed, was one of the great scientific acquisitions of the past century. It is not possible to enter deeply into the subject here. It is sufficient if we briefly outline its salient aspects. Energy is recognized in two forms, kinetic and potential. The form of energy which is most apparent to us is the energy of motion, for example, a rolling stone, running water, a falling body, and so on. We call the energy of motion kinetic energy. Potential energy is the energy a body has in virtue of its position. In its capacity, in other words, to acquire kinetic energy, as in the case of a stone resting on the edge of a cliff. Energy may assume different forms. One kind of energy may be converted directly or indirectly into some other form. The energy of burning coal, for example, is converted into heat, and from heat energy we have mechanical energy, such as that manifested by the steam engine. In this way we can transfer energy from one body to another. There is the energy of the great waterfalls of Niagara, for instance, which are used to supply the energy of huge electric power stations. What heat is. An important fact about energy is that energy tends to take the form of heat energy. The impact of a falling stone generates heat. A waterfall is hotter at the bottom than at the top. The falling particles of water, on striking the ground, generate heat, and most chemical changes are attended by heat changes. Energy may remain latent indefinitely in a lump of wood, but in combustion it is liberated, and we have heat as a result. The atom of radium or of any other radioactive substance, as it disintegrates, generates heat. Every hour radium generates sufficient heat to raise the temperature of its own weight of water from the freezing point to the boiling point. And what is heat? Heat is molecular motion. The molecules of every substance, as we have seen on a previous page, are in a state of continual motion, and the more vigorous the motion, the hotter the body. As wood or coal burns, the invisible molecules of these substances are violently agitated, and give rise to ether waves which our senses interpret as light and heat. In this constant movement of the molecules, then, we have a manifestation of the energy of motion and of heat. That energy which disappears in one form reappears in another has been found to be universally true. It was Joule who, by churning water, first showed that a measurable quantity of mechanical energy could be transformed into a measurable quantity of heat energy. By causing an apparatus to stir water vigorously, that apparatus being driven by falling weights or a rotating flywheel, or by any other mechanical means, the water became heated. A certain amount of mechanical energy had been used up, and a certain amount of heat had appeared. The relation between these two things was found to be invariable. Every physical change in nature involves a transformation of energy, but the total quantity of energy in the universe remains unaltered. This is the great doctrine of the conservation of energy. Substitutes for coal. Consider the source of nearly all the energy which is used in modern civilization: coal. The great forests of the Carboniferous epoch now exist as beds of coal. By the burning of coal, a chemical transformation, the heat energy is produced on which at present our whole civilization depends. Whence is the energy locked up in the coal derived? From the sun. For millions of years the energy of the sun's rays had gone to form the vast vegetation of the Carboniferous period, had gone to form the vast vegetation of the Carboniferous era, and had been transformed, by various subtle processes, into the potential energy that slumbers in those immense fossilized forests. The exhaustion of our coal deposits would mean, so far as our knowledge extends at present, the end of the world's civilization. There are other known sources of energy, it is true. There is the energy of falling water. The great falls of Niagara are used to supply the energy of huge electric power stations. Perhaps also something could be done to utilize the energy of the tides, another instance of the energy of moving water. And attempts have been made to utilize directly the energy of the sun's rays. But all these sources of energy are small compared with the energy of coal. A suggestion was made at a recent British Association meeting that deep borings might be sunk in order to utilize the internal heat of the earth, but this is not, perhaps, a very practical proposal. By far the most effective substitutes for coal would be found in the interior energy of the atom, a source of energy which, as we have seen, is practically illimitable. If the immense electrical energy in the interior of the atom can ever be liberated and controlled, then our steadily decreasing coal supply will no longer be the bugbear it now is to all thoughtful men. The stored-up energy of the great coal fields can be used up, but we cannot replace it or create fresh supplies. As we have seen, energy cannot be destroyed, but it can become unavailable. Let us consider what this important fact means. Dissipation of energy. Energy may become dissipated. Where does it go? Since if it is indestructible, it must still exist. It is easier to ask the question than to give a final answer, and it is not possible in this outline, where an advanced knowledge of physics is not assumed on the part of the reader, to go fully into the somewhat difficult theories put forward by physicists and chemists. We may raise the temperature, say, of iron until it is white hot. If we stop the process, the temperature of the iron will gradually settle down to the temperature of the surrounding bodies. As it does so, where does its previous energy go? In some measure it may pass to other bodies in contact with the piece of iron, but ultimately the heat becomes radiated away in space, where we cannot follow it. It has been added to the vast reservoir of unavailable heat energy of uniform temperature. It is sufficient here to say that if all bodies had a uniform temperature, we should experience no such thing as heat, because heat only travels from one body to another, having the effect of cooling the one and warming the other. In time, the two bodies acquire the same temperature. The sum total of the heat in any body is measured in terms of the kinetic energy of its moving molecules. There must come a time, so far as we can see at present, when, even if all the heat energy of the universe is not radiated away into empty, infinite space, yet a uniform temperature will prevail. If one body is hotter than another, it radiates heat to that body until both are at the same temperature. Each body may still possess a considerable quantity of heat energy, which it has absorbed, but that energy, so far as reactions between those two bodies are concerned, is now unavailable. The same principle applies whatever number of bodies we consider. Before heat energy can be utilized, we must have bodies with different temperature. If the whole universe were at some uniform temperature, then, although it might possess an enormous amount of heat energy, this energy would be unavailable. What a uniform temperature would mean. And what does this imply? It implies a great deal, for if all the energy in the world became unavailable, the universe as it now is would cease to be. It is possible that, by the constant interchange of heat radiations, the whole universe is tending to some uniform temperature, in which case, although all molecular motion would not have ceased, it would have become unavailable. In this sense, it may be said that the universe is running down. If all the molecules of a substance were brought to a standstill, that substance would be at the absolute zero of temperature. There could be nothing colder. The temperature at which all molecular motions would cease is known. It is minus 273 degrees centigrade. No body could possibly attain a lower temperature than this. A lower temperature could not exist. Unless there exists in nature some process of which we know nothing at present, whereby energy is renewed, our solar system must one day sink to this absolute zero of temperature. The sun, the earth, and every other body in the universe is steadily radiating heat, and this radiation cannot go on forever, because heat continually tends to diffuse and to equalize temperatures. But we can see, theoretically, that there is a way of evading this law. If the chaotic molecular motions which constitute heat could be regulated, then the heat energy of a body could be utilized directly. Some authorities think that some of the processes which go on in the living body do not involve any waste energy, that the chemical energy of food is transformed directly into work without any of it being dissipated as useless heat energy. It may be, therefore, that man will finally discover some way of escape from the natural law that, while energy cannot be destroyed, it has a tendency to become unavailable. The primary reservoir of energy is the atom. It is the energy of the atom of elements in the sun, the stars, the earth, from which nature draws for all her supply of energy. Shall we ever discover how we can replenish the dwindling resources of energy, or find out how we can call into being the at present unavailable energy which is stored up in uniform temperature? It looks as if our successors would witness an interesting race between the progress of science on the one hand and the depletion of natural resources upon the other. The natural rate of flow of energy from its primary atomic reservoirs to the sea of waste heat energy of uniform temperature allows life to proceed at a complete pace sternly regulated by the inexorable laws of supply and demand, which the biologists have recognized in their field as the struggle for existence. It is certain that energy is an actual entity just as much as matter, and that it cannot be created or destroyed. Matter and ether are receptacles or vehicles of energy. As we have said, what these entities really are in themselves we do not know. It may be that all forms of energy are in some fundamental way aspects of the same primary entity which constitutes matter. How all matter is constituted of particles of electricity we have already seen. The question to which we await an answer is, what is electricity? Matter, ether, and Einstein. The supreme synthesis, the crown of all this progressive conquest of nature, would be to discover that the particles of positive and negative electricity, which make up the atoms of matter, are points or centers of disturbances of some kind in a universal ether, and that all our energies, light, magnetism, gravitation, etc., are waves or strains of some kind set up in the ether by these clusters of electrons. It is a fascinating, tantalizing dream. Larmor suggested in 1900 that the electron is a tiny whirlpool or vortex in ether, and as such a vortex may turn in either of two opposite ways, we seem to see a possibility of explaining positive and negative electricity. But the difficulties have proved very serious, and the nature of the electron is unknown. A recent view is that it is a ring of negative electricity rotating about its axis at a high speed, though that does not carry us very far. The unit of positive electricity is even less known. We must be content to know the general lines on which thought is moving towards the final unification. We say unification, but it would be a grave error to think that ether is the only possible basis for such unity, or to make it an essential part of one's philosophy of the universe. Ether was never more than an imagined entity to which we ascribed the most extraordinary properties, and which seemed then to promise considerable aid. It was conceived as an elastic solid of very great density, stretching from end to end of the universe, transmitting waves from star to star at the rate of 186,000 miles a second. Yet it was believed that the most solid matter passed through it as if it did not exist. Some years ago a delicate experiment was tried for the purpose of detecting the ether. Since the earth, in traveling round the sun, must move through the ether if the ether exists, there ought to be a stream of ether flowing through every laboratory, just as the motion of a ship through a still atmosphere will make a wind. In 1887, Michelson and Morley tried to detect this. Theoretically, a ray of light in the direction of the stream ought to travel at a different rate from a ray of light against the stream or across it. They found no difference, and scores of other experiments have failed. This does not prove that there is no ether, as there is reason to suppose that our instruments would appear to shrink in precisely the same proportion as the alteration of the light. But the fact remains that we have no proof of the existence of ether. Ch8 Jeans says that nature acts as if no such thing existed. Even the phenomena of light and magnetism, he says, do not imply ether, and he thinks that the hypothesis may be abandoned. The primary reason, of course, for giving up the notion of the ether is that, as Einstein has shown, there is no way of detecting its existence. If there is an ether, then, since the earth is moving through it, there should be some way of detecting this motion. The experiment has been tried, as we have said, but, although the method used was very sensitive, no motion was discovered. It is Einstein who, by revolutionizing our conceptions of space and time, showed that no such motion ever could be discovered, whatever means were employed, and that the usual notion of the ether must be abandoned. We shall explain this theory more fully in a later section. Influence of the tides. Origin of the moon. The earth slowing down. Until comparatively recent times, until in fact the full dawn of modern science, the tides ranked amongst the greatest of nature's mysteries. And indeed, what agency could be invoked to explain this mysteriously regular flux and reflux of the waters of the ocean? It is not surprising that that steady, rhythmical rise and fall suggested to some imaginative minds the breathing of a mighty animal. And even when man first became aware of the fact that this regular movement was somehow associated with the moon, was he much nearer an explanation? What bond could exist between the movements of that distant world and the diurnal variation of the waters of the earth? It is reported that an ancient astronomer, despairing of ever resolving the mystery, drowned himself in the sea. The earth pulled by the moon. But it was part of the merit of Newton's mighty theory of gravitation that it furnished an explanation even of this age-old mystery. We can see, in broad outlines at any rate, that the theory of universal attraction can be applied to this case. For the moon, Newton taught us, pulls every particle of matter throughout the earth. If we imagine that part of the earth's surface which comprises the Pacific Ocean, for instance, to be turned towards the moon, we see that the moon's pull, acting on the loose and mobile water, would tend to heap it up into a sort of mound. The whole earth is pulled by the moon, but the water is more free to obey this pull than is the solid earth, although small tides are also caused in the earth's solid crust. It can be shown also that a corresponding hump would tend to be produced on the other side of the earth, owing in this case to the tendency of the water, being more loosely connected, to lag behind the solid earth. If the earth's surface were entirely fluid, The rotation of the earth would give the impression that these two humps were continually traveling round the world, once every day. At any given part of the earth's surface, therefore, there would be two humps daily, that is, two periods of high water. Such is the simplest possible outline of the gravitational theory of the tides. The actually observed phenomena are vastly more complicated, and the complete theory bears very little resemblance to the simple form we have just outlined. Everyone who lives in the neighborhood of a port knows, for instance, that high water seldom coincides with the time when the moon crosses the meridian. It may be several hours early or late. High water at London Bridge, for instance, occurs about 1½ hours after the moon has passed the meridian, while at Dublin high water occurs about 1½ hours before the moon crosses the meridian. The actually observed phenomena, then, are far from simple. They have, nevertheless, been very completely worked out, and the times of high water for every port in the world can now be prophesied for a considerable time ahead. The action of sun and moon. It would be beyond our scope to attempt to explain the complete theory, but we may mention one obvious factor which must be taken into account. Since the moon, by its gravitational attraction, produces tides, we should expect that the sun, whose gravitational attraction is so much stronger, should also produce tides, and, we would suppose at first sight, more powerful tides than the moon. But while it is true that the sun produces tides, it is not true that they are more powerful than those produced by the moon. The sun's tide-producing power is, as a matter of fact, less than half that of the moon. The reason of this is that distance plays an enormous role in the production of tides. The mass of the sun is 26 million times that of the moon. On the other hand, it is 386 times as far off as the moon. This greater distance more than counterbalances its greater mass, and the result, as we have said, is that the moon is more than twice as powerful. Sometimes the sun and moon act together, and we have what are called spring tides. Sometimes they act against one another, and we have neap tides. These effects are further complicated by a number of other factors, and the tides at various places vary enormously. Thus, at St. Helena, the sea rises and falls about 3 feet, whereas in the Bay of Fundy it rises and falls more than 50 feet. But here again the reasons are complicated. Origin of the moon. But there is another aspect of the tides which is of vastly greater interest and importance than the theory we have just been discussing. In the hands of Sir George H. Darwin, the son of Charles Darwin, the tides have been made to throw light on the evolution of our solar system. In particular, they have illustrated the origin and development of the system formed by our earth and moon. It is quite certain that, long ages ago, the earth was rotating immensely faster than it is now, and that the moon was so near as to be actually in contact with the earth. In that remote age the moon was just on the point of separating from the earth, of being thrown off by the earth. Earth and moon were once one body, but the high rate of rotation caused this body to split up into two pieces. One piece became the earth we now know, and the other became the moon. Such is the conclusion to which we are led by an examination of the tides. In the first place, let us consider the energy produced by the tides. We see evidences of this energy all round the world's coastlines. Estuaries are scooped out, great rocks are gradually reduced to rubble, innumerable tons of matter are continually being set in movement. Whence is this energy derived? Energy, like matter, cannot be created from nothing. What, then, is the source which makes this colossal expenditure possible? The earth slowing down. The answer is simple, but startling. The source of tidal energy is the rotation of the earth. The massive bulk of the earth, turning every 24 hours on its axis, is like a gigantic flywheel. In virtue of its rotation, it possesses an enormous store of energy. But even the heaviest and swiftest flywheel, if it is doing work, or even if it is only working against the friction of its bearings, cannot dispense energy forever. It must gradually slow down. There is no escape from this reasoning. It is the rotation of the earth which supplies the energy of the tides, and as a consequence the tides must be slowing down the earth. The tides act as a kind of brake on the earth's rotation. These masses of water, held back by the moon, exert a kind of dragging effect on the rotating earth. Doubtless this effect, measured by our ordinary standards, is very small. It is, however, continuous, and in the course of the millions of years dealt with in astronomy, this small but constant effect may produce very considerable results. But there is another effect which can be shown to be a necessary mathematical consequence of tidal action. It is the moon's action on the earth which produces the tides, but they also react on the moon. The tides are slowing down the earth, and they are also driving the moon farther and farther away. This result, strange as it may seem, does not permit of doubt, for it is the result of an indubitable dynamical principle, which cannot be made clear without a mathematical discussion. Some interesting consequences follow. Since the earth is slowing down, it follows that it was once rotating faster. There was a period a long time ago when the day comprised only 20 hours. Going farther back still, we come to a day of 10 hours, until, inconceivable ages ago, the earth must have been rotating on its axis in a period of from 3 to 4 hours. At this point let us stop and inquire what was happening to the moon. We have seen that at present the moon is getting farther and farther away. It follows, therefore, that when the day was shorter the moon was nearer. As we go farther back in time, we find the moon nearer and nearer to an earth rotating faster and faster. When we reach the period we have already mentioned, the period when the earth completed a revolution in 3 or 4 hours, we find that the moon was so near as to be almost grazing the earth. This fact is very remarkable. Everybody knows that there is a critical velocity for a rotating flywheel, a velocity beyond which the flywheel would fly into pieces because the centrifugal force developed is so great as to overcome the cohesion of the molecules of the flywheel. We have already likened our earth to a flywheel, and we have traced its history back to the point where it was rotating with immense velocity. We have also seen that, at that moment, the moon was barely separated from the earth. The conclusion is irresistible. In an age more remote, the earth did fly in pieces, and one of those pieces is the moon. Such, in brief outline, is the tidal theory of the origin of the Earth-Moon system. The day becoming longer. At the beginning, when the moon split off from the earth, it obviously must have shared the earth's rotation. It flew round the earth in the same time that the earth rotated, that is to say, the month and the day were of equal length. As the moon began to get farther from the earth, the month, because the moon took longer to rotate round the earth, began to get correspondingly longer. The day also became longer, because the earth was slowing down, taking longer to rotate on its axis, but the month increased at a greater rate than the day. Presently the month became equal to 2 days, then to 3, and so on. It has been calculated that this process went on until there were 29 days in the month. After that the number of days in the month began to decrease until it reached its present value or magnitude, and will continue to decrease until once more the month and the day are equal. In that age the earth will be rotating very slowly. The braking action of the tides will cause the earth always to keep the same face to the moon. It will rotate on its axis in the same time that the moon turns round the earth. If nothing but the earth and moon were involved, this state of affairs would be final. But there is also the effect of the solar tides to be considered. The moon makes the day equal to the month, but the sun has a tendency, by still further slowing down the earth's rotation on its axis, to make the day equal to the year. It would do this, of course, by making the earth take as long to turn on its axis as to go around the sun. It cannot succeed in this owing to the action of the moon, but it can succeed in making the day rather longer than the month. Surprising as it may seem, we already have an illustration of this possibility in the satellites of Mars. The Martian day is about 1/2 hour longer than ours, but when the 2 minute satellites of Mars were discovered, it was noticed that the inner one of the 2 revolved round Mars in about 7 hours 40 minutes. In one Martian day, therefore, one of the moons of Mars makes more than 3 complete revolutions round that planet, so that, to an inhabitant of Mars, there would be more than 3 months in a day. End of chapter. End of book. Thank you for listening.